My name is Daniele Procida, so if you wanted to come to a talk on debugging, you're in the right place. Well, first I'd like to say thank you to the organizers of this conference, the organizers and all the volunteers and the people who have put it on. Thank you for inviting me, and thank you for all the work that has gone into this, because I know how much work that is. So when you see an organizer, remember to say thank you to them. Very briefly about me, I work at Divio. Divio is a Swiss cloud hosting provider for Python and Django projects, so developers don't have to be DevOps or system administrators. Divio is at divio.com. I'm a core developer of the Django project and a board member of the Django Software Foundation. And those are my details. Feel free to drop me a line by email. I don't say anything interesting on Twitter, but you might find me there. And, or just come and talk to me. I've got some discounts to offer people who want a 20% discount for a year on our product, so just come and talk to me afterwards. I'm very happy to talk to anyone. But that's enough about me, because I'm actually here to talk to you about something that programmers are more familiar with, which is tragedy and madness. You should know this picture. This is Landscape with the Fall of Icarus by Peter Bruegel the Elder. And there's Icarus in the corner of the screen, plummeting into the ocean. And you can imagine the fear and agony of that fall, Icarus falling from the sky, terrified, and his father watching him helplessly, and the grief and the loss, and you could think, well, that's a senseless tragedy, an awful, pointless, meaningless loss. And I think that's partly right and partly wrong. A tragedy, if we want to stick with the original meaning of the word from the ancient Greek, is a dramatic form. It's the story of a downfall or a loss. So on that basis, tragedy is always meaningful, because stories, by definition, are meaningful. A tragedy is a story that makes sense of some dreadful occurrence, like somebody falling to their death out of the sky. And it's something that allows us to find some meaning in that terrible event. So we've got two things. We've got what happened, and we have the story of what happened. We have the fall of Icarus and the story of the fall of Icarus. And what happened maybe has no meaning, but the story has a meaning. And in the story we can find, for example, warnings about hubris, about foolish pride, about not paying attention to your father's warnings, or about how the world continues as you fall to your end. So if I can put it another way, which I'll come back to, Icarus's time belonged only to him, and it's gone and he's gone. But we still have the story of the time, the record of the time, and that is ours to keep and to learn from. So there's the time and there's the record of the time. And what I'm interested in is what we can learn from the record of the time. Programming, or really debugging, which is the part of programming that I want to talk about today, is something that can drive you mad. Now, according to Einstein, Insanity, Madness, the definition of madness is doing the same thing over and over again and expecting different results. Well, except it wasn't Einstein who said it, it was apparently Rita Mae Brown. Maybe it wasn't actually Rita Mae Brown, maybe it was Mark Twain, or maybe it's an ancient Chinese proverb, and actually, I never did find out who came up with this definition. But you get the point, and you're programmers, so you recognize this. By the way, if you're standing at the back, there are plenty of seats at the front, so come and take a seat at the front. I'm not going to pick you out for audience participation, and I don't bite. You're programmers, you recognize this. It's familiar. Can you put your hand up if you found yourself doing the same thing again after running into unexpected behavior, running exactly the same code in exactly the same situation, as if you might get a different result? Well, yeah, come on. Sometimes I do it before breakfast. So there's something mad about this, and it's a madness. It's an experience that programmers are familiar with. Well, what's going on? What is this madness that afflicts programmers when they sit there at the controls of their machinery, doing the same thing again because the results weren't what they expected or wanted, when they do it again and still watch in disbelief when the program crashes, when, despite the evidence of their own eyes, all they can say is, damn it, this can't be happening. On the 31st of May 2009, Air France Flight 447 took off from Rio de Janeiro to Paris, and 3 hours after takeoff, it encountered icing conditions. And ice crystals began to accumulate in in all of the pitot tubes that measure air pressure and therefore airspeed, causing them to give inconsistent readings. And this caused the autopilot to disengage. And a warning sounded in the cockpit. Because of the turbulent conditions, Pierre-Cédric Bonin, who was the pilot flying, had to correct the plane's attitude, and as well as adjusting for roll, he pulled back on the stick, causing the aircraft to climb and lose airspeed. And within about 60 seconds, the icing event was over, and the instruments were reporting normally. However, the plane had climbed to its maximum altitude, and it had lost airspeed, and it was losing lift, and it began to stall, which means it's no longer flying because the wings are no longer providing enough lift to keep it in the air. The stall alarm sounded in the cockpit, and the aircraft fell, and the pilots fought the controls down towards the Atlantic Ocean, desperately trying to make sense of what was happening. And all the while, Bonin kept pulling back, trying to climb, not realizing that the plane was in a stall and not trusting the instruments that were in front of him. His colleague, David Robert, was in the cockpit with him. The captain, who'd been on a rest break, was called back immediately into the cockpit and sat behind the two pilots. And the stall warning blared out nearly 80 times. And finally, just a few thousand feet, in aviation, altitudes are measured in feet, a few thousand feet above the water, the first officer, David Robert, and the captain, Marc Dubois, finally realized what Bonin had been doing, and they correctly put the nose down so that the plane could pick up speed and recover. And it was too late. And the airliner smashed into the Atlantic Ocean, and all 228 people on board died. That's one of the last things that you can hear desperately on the cockpit voice recorder. So this incident, this accident, has a hold on people's imagination. It has assumed the status of a myth, like the story of Icarus, or maybe like the story of the Titanic. You know, that it's a tragedy in which people think that there must be some kind of deeper truth or meaning in it. How can we explain how one of the safest, most reliable aircraft in the history of aviation came to fall out of the sky? Because there was absolutely no reason for that Airbus to crash. The crew were not incapacitated. The engines were working. The plane responded correctly to all the controls. There was nothing wrong with the plane. Apart from a brief sensor error, it functioned normally, all the way down to the ocean. And it's something that can give you the shivers just to think about it. Partly because, you know, most of us travel in airplanes, and you know this could be you. Partly it's because you think about those doomed 228 souls falling out of the sky. But also I think it gives us the shivers, because it's not just a story of something that went wrong, it's the story of something that went madly wrong. It represents a breakdown of rationality itself. it's a glimpse into thinking that seems to have gone mad. It's like staring into an abyss, and we find that very hard to look into. This is Laurie Anderson. You should listen to her records, but maybe not just before you get on an aeroplane. She's obsessed with flying. In an air crash, there are two times. There's the time, and there is the record of the time. There's the time that belongs to the human world, the time, our time of flesh and blood and fear, the time we live in here and now. And there's that other time that belongs to this other world, the world of aviation and the aeroplane and its systems and numbers and the technology, in which the plane will somehow exist even after it has been broken apart in a disaster. There's our time that we live in now. It's contradictory and confused and counted out in remaining minutes and maybe seconds, and the time that will be pieced back together again afterwards in the investigation and preserved forever, captured by the flight's data recorders. So we have the time and the record of the time. And when our time comes to an end, maybe some shadow of it, something of it can be recreated from that record, just like in an disaster investigation, they kind of recreate the aircraft out of its pieces. But this time, our time will be gone and can never be recovered. Only the record will remain. And our time unfolds just once, and it moves on in one direction inexorably towards its conclusion. But the record of the time can be played back over and over again, forwards or backwards, slowed down or stopped. In our time, Air France 447 is gone, and all those people are gone. In the record of the time, we can suspend the plane in its fall. The passengers unaware or even asleep, the pilots fighting the controls, the passengers unaware of the madness that has taken over in the cockpit, unaware that Pierre-Cédric Bonin is doing the same thing over and over again and expecting a different result. And people like to talk about pilot error, but it's a term that should rarely be used. It's not very informative. The record of the time, the reconstruction of the apparently irrational judgments and decisions in the cockpit plays out like a story of insanity, but that's also another unhelpful term that's judgmental and unrevealing. And aviation has a much better name to place upon the record of the time. And that is loss of situational awareness. Bonin, Robert, and Dubois lost situational awareness. And this is what happens when a pilot loses the true picture of their situation. It takes many forms and it unfolds in many different ways, but the basic idea is that when you lose situational awareness, everything you need to know can be staring you right in the face. But because of some contradiction with your expectations, you'll fail to understand what they're telling you. And in aviation, loss of situational awareness can be deadly. It's a kind of cognitive breakdown, which has a number of notable characteristics. They're all closely related, and they all play into each other. And blind spots, faulty mental models, misjudging cause and effect, and poor decision-making. I'll talk more about these later. But the question I want to explore is this. Does the same kind of madness, the same kind of cognitive breakdown afflict programmers and pilots in the same way when they make apparently irrational judgments and decisions? And I think in order to answer that, it's worth looking at programmers and programming more closely to understand what actually is it that they are doing. So what kind of thing is programming? Well, fortunately, not many people think that programming is a science. A few people do, and they're wrong. So don't get confused by the existence of, for example, computer science. That's concerned with computation, not with programming. Programming is much more like engineering or flying a plane. So some people think that engineering and flying planes are sciences, and they're also wrong. They're not. Programming and engineering and piloting are skills, crafts, or arts, what in ancient Greece would be referred to as examples of techne, which is the root of our modern word technology. And in fact, one of the examples that Plato uses often of techne is of piloting a ship. And we can find various interesting parallels between programming and piloting. For example, if you're familiar with pair programming, then that has a direct relation, a direct counterpart in the two-pilot cockpit, where you have one pilot flying and one pilot monitoring. So the pilot flying is the one who operates the controls, and the pilot flying is responsible for managing checklists and communications and overall flight operations. And in this talk, I'm interested in finding some more parallels about the things that happen, about what happens when things go wrong. So in nearly all crafts, in all skills, you'll find two distinct activities, two parts or phases that are part of the cycle of exercising the craft. Two different activities. So we have the craft of in programming, we have programming itself, and then we have the debugging part of programming. We have the creative act of programming and the troubleshooting activity of debugging. We find these in all crafts. You'll see them that in the primary activity, it's synthetic, where things are brought together. In the secondary activity, it's analytic, where they're taken apart to find out what's happening. Assembly versus disassembly. In the primary activity, we're moving forward to an aim. In the secondary activity, we move backwards from a problem. Our thinking in the primary activity is imaginative and goal-oriented. In the secondary activity, it's logical and problem-oriented. In the primary activity, we ask questions like, how can we get there from here? In the secondary activity, the question is, how did we end up here? Let's make something happen on one hand, and how did this, or why isn't it happening on the other? So you'll find this in every kind of craft, whether it's motor mechanics or surgery, piloting or programming. The work of the programmer, however, is a little bit unusual in that we spend so much time in that part of the cycle compared to most other crafts. And that's the part of programming that I'm interested in right now. Not programming as a whole, not in the programming activity of programming, but in the debugging activity of programming. And I'm interested in it partly because the primary activity, the synthetic, creative, forward-moving part, gets a lot of attention as a discipline. As an activity, programming has developed methodologies and models and frameworks and paradigms and practices, and a great deal has been said about how teams work, how work can be planned, managed, and executed, tested, delivered, and reviewed, and so on. But about debugging, very little gets said or even thought. And that's odd, because debugging is so important to programmers and takes up such a lot of their time and energy. So I think there are some really important reasons why that secondary activity of debugging turns out to be so much more significant in programming than in most other crafts. Firstly, programming is a creative craft, like writing. So when you're let's say that you're preparing a meal or performing surgery on someone. That's not in its nature a creative activity. You want the person who's preparing your meal or performing the operation to have done it before, to have done it correctly, to know exactly how it's going to unfold. You don't want somebody to be experimenting while they're making your lunch. Yeah? That's not why you go to restaurants. You want successful outcomes. Whereas programming or writing, or writing, those are creative crafts. You don't know when you start what the outcome's going to be. You're not doing something that has been done before. You're creating something new. A second characteristic of programming, that in programming, when you run into failure, it's unarguable. You don't sit and argue with your traceback and say, well, no, actually, you're wrong. It does work. If somebody reads your writing and says, well, I don't think this passage really works, so you say, no, you've misunderstood. You've misunderstood my writing. You can blame the reader if you're a writer. You can't do much blaming when you're a programmer. If your patient dies on the operating table, then you can't argue with that. And programming is like that. You can't argue with the outcomes. In programming, try again is nearly instantaneous and cost-free. If you've built a bridge or a dam and it fails, you don't say, let's try that again. In programming, you just hit the up cursor, the up arrow, and hit return to run it again in the terminal, and it costs you nothing. To get feedback in programming is also instantaneous and nearly cost-free. You think, well, okay, it's completely half-baked, I have no idea whether it will work, let's try it. That's not how they do things when they're building aircraft, for example. And finally, debugging is a private affair. It's like being sick or realizing that your relationship is going bad. It's a misery that you suffer in silence. Yeah? Programmers love talking about what they do, that what I'm going to do, what I've done. They'll talk about debugging afterwards. I had this battle with this terrible bug and I sat up all night, and they'll boast to you about their war stories of the bugs. You try and talk to a programmer when they're fighting with a bug, when they're losing the battle of debugging. They'll have their headphones on and their faces to the wall because they don't want to even look another person in the eye. They want to suffer that misery in private. So all of these form part of a potentially vicious cycle in which the response of the programmer to an error is to try again. And it's a short cycle in which they have no time to step away from it and maybe talk to somebody else and get another perspective because they want to suffer it by themselves. They're doing something new, so they've got to feel their way. It's not like the surgeon or the cook, the chef, who knows what they're going to achieve and how to do it. And they don't have any room for arguing about whether it worked or not. So it forces the programmer into a vicious cycle in which, there we are, programmers, debugging, finding ourselves doing the same thing again as if we expected a different result, fighting the controls. And you could say madness, but we've already found a better way to describe it. So what we can say is that we can see an inherent tendency in debugging towards cognitive breakdown. That is, debugging itself provokes loss of situational awareness. I'm arguing that the activity of debugging is responsible for producing the same kind of cognitive breakdown that tore Flight 447 out of the sky. So you're a web application developer. You're trying to restart a web application that's crashed. You've checked the logs, you've flushed the caches, you've restarted the application. You've restarted the web server. Now you're actually logged in, you're SSH'd into the web server with a terminal inserting print functions into your code, desperate for any clue. You think, damn it, this can't be happening. And the next thing you know, you're in the grip of madness, doing things that you would never dream of doing normally, like changing production code on the fly or trying to reconfigure the web application gateway. And finally, you discover what is happening. You have been doing all these desperate and futile things on the wrong server. You were typing the commands in the wrong terminal window. and you were desperate for clues, and all the clues were there, and you didn't see them, and you couldn't see them because you were too busy fighting the controls. You lost situational awareness. You're laughing now, but it's not so funny when it actually happens, is it? Yeah? Or you're debugging some complex algorithm that was working until yesterday when you made some minor and insignificant changes to it. And you know your algorithm inside out because you've been living inside it for a month. And now somehow its logic is collapsing all around you. So you take it apart, piece by tiny piece, checking and changing parts of it that you know can't possibly be related to the failure. Changing it so much, in fact, that your own mental model of it starts to break down. And the feeling is one of incomprehension and outrage and anger, as if you've been robbed of something, and in a way something has been stolen from you. You think, damn it, this can't be happening. And finally, you realize that in amongst the minor and insignificant changes that you made, one of them caused your algorithm to receive a different data set from the one it was expecting, data that had now been processed by something else in the meantime. So you dived deep into a debugging rabbit hole, chasing after a completely irrelevant solution to your problem. There was absolutely nothing wrong with your algorithm, but you were fighting the controls and you lost situational awareness. And then you fly your plane into the ocean, telling yourself that this can't be happening. Loss of situational awareness is the enemy of the pilot and the programmer. So what can we do about it? When it happens to us, when it happens to programmers, it makes us look and feel foolish. When it happens to pilots, they die. So unsurprisingly, aviation has developed very effective strategies to mitigate the loss of situational awareness, to prevent its loss in the first place, and to recover it when it starts to fail. And what they do is target the kinds of cognitive breakdown that characterize loss of situational awareness. So remember, we briefly mentioned these characteristics of cognitive breakdown. So blind spots. Your eye has a blind spot where the optic nerve leaves. So if you close one eye at the right distance and look at one of these dots, at the right distance, you will be unable to see the other dot. I mean, it's literally impossible for you to see the other dot because your eye will not receive that, that visual information. Blind spots are deadly. A blind spot doesn't just obscure the thing you might like to be able to see, it obscures its own existence. If you have a blind spot, you can't even tell that you have a blind spot. And we all live with blind spots, and new ones can appear in our perception and cognition at any time. And the only way to see past a blind spot is to introduce a new perspective, either by changing our perspective or bringing in the perspective of another observer. One of the reasons why we have two eyes. Faulty mental models. We all rely on our mental models of the world. We have to be able to internalize the world outside in order to be able to deal with it. It's our subjective representation of reality. And the more complex the part of the world that we need to deal with, the more complex our mental model needs to be. When our model starts to break down, it has to be rebuilt based on the world, based on something objective, on objective reality from outside our subjective representation. So German's a very interesting language. It has two words for object, Ding, and the equivalent of English thing, and Gegenstand. Gegenstand means literally something like against stand or stand against. Objectivity, objects are things that we can stand against, some other thing that is outside ourselves, that's not ourselves, but we can stand against them to find out where we are in the world. We don't need the full, true, complete picture of reality. We just need something to stand against so we can start to recalibrate and remeasure and refine and relocate ourselves, a piece of the world with which to rebuild our faulty mental model. misjudging cause and effect. So we don't actually see causality. We see successions of events, and we apply judgments to them. We say, this was the cause of that. We say causality is at work in nature. We judge that our act was the cause of some effect that we see. Now, this is a difficult enough business at the best of times, but when we're in complex and stressful situations, it's very easy to make the wrong judgments about cause and effect. In Flight 447, the flight computers alerted the crew to the stall. But when Bonan pulled back on the control stick and the nose went up again, the angle of attack increased so much that the flight computers were receiving such anomalous data that the stall warning stopped because they just couldn't process what was happening. When the warning stopped, he thought, oh, great, we're recovering, and he would stop pulling back, and the plane nose would come down, and it would start to recover. And then, of course, the stall warning would go off again, because it was still stalling. It was just that it was on its way to recovery. So he pulled back again, and then the warning would stop. So he was trapped in this tight, horrific feedback loop of cause and effect, in which the effects were 180 degrees out of phase with their causes, with his actions. We have to make judgments and observations. They're all we have to work with, because we don't have direct access to causality in the world itself. But rescuing our judgments about cause and effect means pulling them out of these tight, stressful loops by making them clear and explicit so they can be checked and corrected. And finally, poor decision-making. Our decision-making processes need to be exposed, need to be made explicit so they can be checked. Private decision-making is almost always of poor quality. Bonan's reasoning about what was going on, if he had spelled it out to the other members of the crew, would have been immediately exposed as faulty. And as panic set in, his actions became more and more irrational. Even in that context, his decisions, his responses were of poor quality, and they went unchallenged because they stayed inside his head, where they couldn't be corrected. And the rest of the crew made poor decisions too. They made decisions that were revealed in actions or implicit in their remarks, but they were never fully brought out into the light by being made explicit. So aviation has spent over a century learning how to deal with these problems, and its lessons are woven into every pilot's training. In aviation, cognitive breakdown is addressed through the employment of very simple, practical procedures. Pilot training doesn't give pilots supernormal, calm, confidence, competence, powers that ordinary people don't have. It gives them processes and procedures. The safety and competence of pilots is founded upon completely ordinary skills and practices. Concrete steps. For example, checklists. In aviation, everything is on a checklist. It doesn't matter how many times you've done it before. Even if you've done it several times that day, you'll work your way through a checklist. This is a 747 freighter checklist. It'll be on a card in the cockpit for normal operations. This is for the primary activity of flying, the normal activity of flying. You know, you can't really read it so well, but before starting, prior to pushback, all the way down to landing and turning off the engines. And here are a couple of pages from an A330 quick reference handbook, the same aircraft that Bonan was flying. This is for the secondary activity of flying, the debugging part. This is the can you read that? This is the emergency procedures quick reference book. There are checklists for everything. As soon as something goes wrong, both pilots have one. They will fish one out and refer to the appropriate page, hundreds of pages. Only for the briefest moment should the pilot rely on their own resources, their memory, and their training to address a problem. Then they should pick up the or the pilot not flying should pick up the handbook and find out what to do. Instead of picking up the quick reference handbook, the crew fought the controls. A checklist serves as an alternative perspective. It's something that's outside you. Your memory and your judgments and assumptions and your reasoning may all be faulty, but when you're following a procedure that requires you to check and confirm things, a checklist helps you make that step outside yourself. It helps rebuild a mental model, particularly the parts of it that we might pass over in a hurry when we're stressed. It offers something to stand against, something objective. Now, we do tend to use checklists a little bit in, when we're software developers for things like for things like system operations, deploying a project or making a release, but that's about it. In programming, I've almost never seen checklists used. And in bugging, I have never seen a checklist used. Maybe it's time to start. Communication, the act of passing something to another person, usually information. In aviation, it's always verified and explicit. Explicit communication addresses all the elements in cognitive breakdown. In aviation, it works like this. I'm flying, and I'm going to hand over control to my co-pilot, say, you have the controls. And my pilot will reply, I have the controls, so that I know, and they know that I know. If I'm the pilot not flying, the pilot monitoring, I'll say, okay, descend to flight level 350. The other one will say, descending to flight level 350. So we're always verifying explicitly what we're doing. This gives us what someone else, someone who is not us, is thinking and doing. It rebuilds and repairs mental models. Even the act of describing what we're doing and thinking out loud helps us rebuild our own mental model, because it forces us to set it out and prevents us just skipping over it. You know, if you say something that's rubbish, you realize it in a way that you don't realize when you just think something that's rubbish. It makes actions and decisions clearer, helping reconnect cause and effect correctly. And it exposes the thinking processes to others. In Flight 447, a communication breakdown was part of the cognitive breakdown. And you can read that and weep. So Robert is saying, climb. This is just before, this was 45 seconds before they hit the ocean. Climb, 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 climb. And Bonan says, but I've had the stick back the whole time. And then the captain in horror says, my God, no, don't climb. He suddenly realizes what's been going on. And Robert says, descend, give me the controls, give me the controls. And that was too late. Bonan had been pulling on the stick, trying to climb. And actually, Robert had been pushing forward on the stick, but the system was in dual input mode, so it averaged the two inputs. And Bonan hadn't said what he was doing, and Robert hadn't said what he was doing. Neither of them had made their actions explicit, so no one in the cockpit knew what the other was doing or thinking until it was too late. And we see this all the time in debugging. It certainly happens to me. I can have a struggle with a problem for hours, finally give up, go and ask someone for help, maybe on IRC, and by the time I finish describing the problem, the answer formulates itself in my own head. I don't know if you can read this. This is just from IRC and the Django IRC channel. Someone says, I've been spent 3 hours bashing my head against it, and then as soon as they ask the question, I figure it out. That's what explicit communication does. You might not have a fellow programmer to explain your problem to. You might have to talk to the wall, but it works. 90% of the work to finding a problem can often be found in describing it. And the other thing that we can do is just stop. Stress and panic drive us into tighter loops of bad decision-making. Now, one thing that aircraft do really well is fly. An airline in particular wants to do nothing more than fly level and in a straight line. Had Bonan let go of the controls when the autopilot disengaged, well, the plane may have deviated from its course a little bit or lost a bit of height, but that would have been the most significant outcome. At almost any point in the next few minutes, he could have simply stopped what he was doing, and the aircraft would have recovered its attitude, its speed, and lift. Don't just do something, sit there. It's a Zen joke. So simply doing nothing allows an aircraft to recover, but also allows a pilot to recover. Now, a pilot can't do nothing indefinitely, but it's possible for much longer than you think, even in unexpected situations. As programmers, we can do nothing almost indefinitely. We can get away from the computer and leave it for 10 minutes, half an hour, and come back in a week if we want to. And we'll find our program waiting patiently for the next input, in the same state as when it crashed or gave the unexpected results. There's no need for us to do anything. So often we should do nothing. Often the best thing we can do is to stand up and get away from that code. So I've suddenly solved more problems while falling asleep or riding my bicycle or mowing the lawn than I ever did by sitting there in front of the computer fighting the controls. And I've definitely done less damage that way as well. So we can do all of these things as programmers. We can adopt checklists. We can communicate explicitly, improve the way we communicate, so we do nothing without exposing it to another person. We can stop fighting the controls. And I think that actually this one is the most valuable of all. They're all ways of stepping away from our failing perspectives, ways of stepping outside ourselves, finding something else in the universe to get a grip on, to stand against. They're ways of resetting failed thinking and preventing bad judgments and decisions. And they can work in programming the same way they work in aviation, and they do work in aviation. We've been talking about Flight 447, not because something like that happens every week, but because it was a staggering, extraordinary, once-in-a-lifetime case. Flying on an airliner is an outstandingly safe way to travel. In the meantime, other industries like surgery or nursing and the nuclear industry have also been adopting the same kinds of strategies and techniques that aviation has developed to keep it safe and make it safer. Programmers love to talk about programming, about the theory and practice and methodology of programming, but they never talk much about the debugging part of programming, as though it might be an embarrassing private misery. And I think that really needs to change. As I said, in an air crash, there are these two times. There's the time, and there's the record of the time. And in aviation, they confront the record of the time. They rebuild it painstakingly. It's scrutinized and replayed endlessly so that it won't be repeated in another terrible loss. And we never do anything like this in programming. We tend not to dwell on our programming failures, and we don't like to confront them in the same way. And it's strange because we're caught up in the time of debugging so much, so often, and so deeply, and we pay so little attention to the record of the time. But aviators do, and we can learn from their lessons without paying their price. We can make use of their techniques that serve them so well, that help resist this common enemy, loss of situational awareness and cognitive breakdown. And the good news is that these are actually really easy to adopt and simple to implement. So the next time you find yourself thinking, damn it, this can't be happening, you can try one of these, probably by stop doing what you're doing. You can start doing them right now. So they're there, they're available for us to use. I don't want to pretend it's so easy, because those things work in aviation because they're built into aviation at every single level, not just because individuals adopt them after a 45-minute conference talk. Aviation is safe because they're a defining part of its culture and processes. The truth is that as individuals probably will only get so far. There's only so much an individual can do. The individual pilot's use of those techniques is made effective because they're part of a systematic approach throughout the entire industry. They're systematic, cultural, and fundamental in aviation. So I think probably our industry needs to change. And maybe I'm pessimistic, but sometimes I think it might not. Sometimes I think that until our debugging mistakes routinely kill us, our colleagues, and our customers, our industry probably won't change because it simply won't have a motivation to change. But we can still try. So thank you very much. That's the end of my talk. If you have any questions now or later, I'd be really happy to answer them.